Then let's go back to the what we left over last time, right? So we try to look at the noise generated by a resistive network. We consider this network, which is a potential divider. You go through the KCL, KVL, you find that V out, if I have an input here, V out equal to R2 divided by R1 plus R2 times V in. Okay, this is simple, right? Now I want to analyze the noise, analyze the noise generated by this circuit. Okay, this is a circuit. Okay, so what I will do, because it's small signal, I can do superposition, and also I don't need to care about V in now because I just want to know the noise. So I will just put 0 at V in. So as a result, I have a ground to there, right? So then these two appear to be parallel because they have the same node and they have the same grounded node. So this is just R1 parallel R2, right? And when we write this, when we draw it in this way, we know that this is a non-ideal resistor, which means it has noise. To explicitly show that it has noise, we can redraw it by an ideal R1 parallel R2. Now we assume there's no noise from here, but we put all the noise as this voltage source. And we know that the thermal noise of a resistor is 4 kTr. And the R here is R1 parallel R2, right? So this is the 4 kT R1 parallel R2. And again, what is it? This is the power spectral density, PSD. This one, S of x, Sx over Vn squared bar, right? So we can say Vn squared bar equal to 4 kT R1 parallel R2. This is a function of frequency. Also, it does not depend on frequency. It is a constant, but it's still a function of frequency. It just turned out to be constant because this is a white noise. Okay, so that is one way to find out the noise generated by the resistor. We can use another way just as a instructive purpose, right? So I will use superposition. What I do is first I assume R2 is ideal and only assume that R1 has noise. Then we just draw out the network. R1 becomes ideal with 4 kT R1 as the Vn1 square bar. Okay, and let's find out what is V out n square. Means that what is the output noise due to this noise, right? Again, as we said, then this is the power, but we can take the voltage value by using the square root, right? So then the relationship of the output voltage, root mean square, like the root mean square sense, right, will be equals to R2 divided by R1 plus R2 times the voltage. But we care about power now, right? Because we are talking about noise, not the voltage at a certain time or at a certain frequency, right? So as we mentioned earlier, then you just square everything, right? So the output voltage power spectral density equals to this transfer function square R2 divided by R1 plus R2, right? And times the input power, right? And so the input power is 4 kT R1. I put it here, right? So this one gives us the output noise power due to the noise from R1. Then we consider R2. This time we assume R1 is ideal, right? We are doing superposition. Superposition means that we assume the excitation one by one and then add them together later, right? So now R1 is ideal, so no noise source, but R2 has noise source, and since it is R2, so it's 4 kT R2. And our question is, at this output node, how much noise do we have? We use the same equation, but this time voltage source is here, so in terms of potential divider, it is going to be R1 divided by R1 plus R2. Again, we square it because we are talking about the power, not the voltage, right? If voltage is just a voltage times the transfer function equal to output voltage, right? But power, so we square it. So very similar to the previous result, it is V0 N2 square means the output noise power due to the second noise equals to this transfer function times 4kt R2. Okay, and then we use superposition to add them together. So you add these two together, 4kt, 4kt, they share, so we take it out, right? Then I have R1, R2 square, R2, R1 square, and then divided by R1 plus R2 square. You go through the math, you get that this is 4kt R1 parallel R2. It is exactly the same as this one, right? Good. So now we know how to calculate the noise. We need to learn something new called signal to noise ratio for this circuit. What is signal to noise ratio? Easy to understand is how signal to noise. In the numerator, you put the signal power. In the denominator, you put the noise power, right? So this is very important in any circuits because if your signal is not much larger than noise, you cannot get the signal correctly. Just in a very noisy restaurant, you need to shout in order to talk to your friends. Otherwise, your friend can only hear the noise, right? And this is the definition. Memorize it. But what is signal power? Again, it's just the voltage square. Now, again, last time we talked about this already. A real power is going to be V squared over R. But here we don't do that. Why? Because we normalize it to 1 ohm, right? We even don't consider the unit. So the real power needs to be renormalized depending on your system, maybe 50 ohm, 100 ohm system. But here we just talk about the voltage square so that we don't need to worry about the resistance. Okay? And then you normalize it when you need it, right? So signal power, of course, is V out square. You look at this circuit, right? It is again superposition. We can ignore the noise when we calculate the output because they all small signal. Then, of course, it is V1 times V2 divided by V1 plus V2 square. First of all, we mentioned this earlier already, right? V out equal to V in times R2 divided by R1 plus R2. Then the square, you just square them. Then you get this term, signal power. That is the power you get. So what is signal to noise ratio? I already know what the noise power is, right? We did that here, 4kt R1 parallel R2. So S and R is this term divided by this term, okay? So I let you please try to go over the math yourself. It's not difficult. R1 parallel R2 is just R1 times R2 divided by R1 plus R2. Pause it and see if you get what I have here. Basically, it's this. If I want to increase the signal to noise ratio, I want to make this term big. What can we do? Increase Vn, Vin. Of course, just like what I said. If it's very noisy, just speak louder so your friend can hear you in the restaurant, right? Or reduce the temperature. Why? Because when you reduce the temperature, you have less noise, less thermal noise. You can also increase R1. Right? Reduce R1 because R1 is the source of the noise. But when you reduce R1, of course, you need to reduce R2 also to maintain the function of the circuit. Okay, so this is the signal to noise ratio.